Thanks. Okay, let's get started. So last two lectures we talked about classical aspect of special relativity, right? Basically, we talked about how to think about Poincare invariance, and then we saw that quantum mechanical sort of implementation of Poincare invariance, meaning unitary operators associated with any element of a Poincare transformation, can be expanded for infinitesimal transformations in terms of generators. And then we basically worked out that those generators has to fulfill algebraic structure known as a Poincare algebra. We haven't discussed yet the representations of those things yet, which we will spend some time at some point. And in fact, just to say that irreducible representation, meaning any representation that you cannot break further down to a smaller pieces, those are nothing but, in a sense, a practical definition of a particle. Okay, so there's a Poincare transformation, and you want that the physics respect the Poincare transformation. Meaning, if you do the experiment here versus there, you hope that the physics law is the same, right? If you do the experiment today and tomorrow, time translation invariance, you hope that the physics doesn't change, right? Et cetera, et cetera. And if you ask, what are the sort of entity in this universe that manifestly fulfill all set of Poincare transformations in a proper way? And as we will talk about at some point, there is notion of representations, meaning it just captures nicely, it basically transforms nicely under all those Poincare transformations. And there's a notion of irreducibility in the sense that, given a representation, you cannot break further down to small pieces. Those are actually best entity to be called a particle. And if you had experience with the physics, if you think about the particle, what are the quantities you attach to? The first thing might be mass. What about the mass? There's electron mass, okay? And then another thing could be spin. If you learn a little bit more about physics, right? Mass, spin. And you can get fancier, you might say, oh, what about the electric charge? Okay, that's also another good thing to use and to label particles. But you can ask yourself why these are the good quantum numbers, good labels you can use to characterize a particle, right? And there's a mathematical reason behind this. And one of the goals is obviously to develop why those are precisely, exactly good quantum numbers we want to use to label particles. But we haven't developed it yet, so we will develop. Before I jump in today's lecture, any questions from previous lectures, previous content? Okay, good. So then let's just jump in. So now that we understood a Poincare transformations and then, yes,
I have a previous lectures context.
저번
시간에 교수님께서 J를 U 인버스로 해서 람다 J로 바뀌는 걸 보여주셨는데,
yes.
계산을 해보니까 두 가지가 있는데, 하나는 람다 인덱스가 반대로 나왔고,
yes.
와인버그에서는 교수님과 같은 결과인데, U의 인버스 순서가 반대라서 와인버그 대로 해도 람다 인덱스 순서가 맞춰줘야 되고.
You mean the why label is that or versus that?
네.
Okay, so your claim is I don't know. It should be one way or the other, but you think it should be a nicely contracting version.
끝나고 한번.
Okay. Okay, so today we will try. So today what I'm going to discuss is that we will try a simple thing or zeroth order thing first. Okay, so we try. Let's smash quantum mechanics into special relativity together, okay? And see where things can fit, okay? So, so what we are going to try is the following thing. So we will try. So for recall for non-relativistic quantum mechanics, okay? For a particle with mass m, you're gonna try. Oh, here's my lovely Hamiltonian. You might say, oh, here's my momentum operator that I know, right? And then you say, oh, I learned that there's momentum and the space position operator, and they have to quantize according to this relation, right? Good. This is all nice story, and in this case, so I'm still talking about non-relativist quantum mechanics. In this case, what you're gonna say, well, this form of Hamiltonian shows you manifestly that momentum operator commutes with the Hamiltonian, as you see here, which means that the momentum is one of the conserved quantity. So therefore, you can use as an eigenstate, momentum eigenstate, such that it takes, so here I'm just describing as if it's a one-dimensional, but obviously you can generalize to the three-dimensional, no problem. So this may be your perfect, complete set of the basis for your Hilbert space, and then you can define a open normality. So in that sense, this is also quick summary of quantum mechanics. Right? So you may impose open normality. So here, let me switch to vector notation, just in case, because I'm going to do that momentarily. So you might have done that. Okay, let me take physics is going to talk about open normality. Okay. Some of my friends may not like it, but this is best we can do at the moment. And then you can also finish the discussion by imposing completeness relation. So completeness says that sum of this should be act as an identity operator on the Hilbert space that is spanned by a full set of this motion eigenstate. Okay, so here we can use this as an eigenstate for Hamiltonian as well because of this. Okay, that's what you're gonna do. Then any state lives in this physical Hilbert space. Obviously, what you do, you can expand in terms of this. Right? And so you may call this to be this, and you might say this is a either profile or wave function, momentum space wave function. Okay, so that's all you hopefully are familiar with. Now, suppose you knew this, and suppose you learned about the special relativity, and then Lorentz for Poincare. And then suppose you want to describe for a relativistic particle with mass, again, m. You know that the energy of this particle has to satisfy in natural movement once again this relation. So that you know. And suppose you want to have some quantum mechanical description of this particle. Okay? Here you successfully describe a non-relativistic particle quantum mechanics, right? So here we're gonna just try some reasonable thing. And the basic lesson that we want to extract out of this exercise is this a good trial that I'm going to present to you, and where and how things will fail. Okay, so you have to be critical every step I'm going to try and think about at what stage things can possibly fail. Okay, so here we will try a dumb thing because we don't have any better idea. So what might be the relativist version of Hamiltonian? Well, let me try a square of momentum operator. So here, by which I mean really three-dimensional version. And then let's take a cube. Let's try it. Why not? It looks reasonable. So then, again, you can hope to see that momentum eigenstate might be a Hamiltonian eigenstate, right? And then you can hope to do a quantum mechanics. If I have a state, it can evolve according to this Hamiltonian. And I'll let you think about how this can make sense and how this might be a Hermitian operator. Okay, I will invite you to think about that. But naively then, if you try to set up this way of doing quantum mechanics for this relativistic particle, then it looks like, given a state, now the state at time t will evolve if you exponentiate according to this. So here this Hamiltonian is time independent. I'm assuming this is also time independent. So I can just exponentiate, and then we might do this kind of evolution, which looks like a nice unitary evolution. So naively, at least naively, so from this chain of arguments, at least naively, quantum mechanics part is fine. So I literally tried the dumbest possible things, right? There is no reason you try fancy stuff. Okay? You must say, I have heard of Droxy. What happened to that? What is that? Right? At this level, you don't have to just grab whatever fancy word you ever heard. Just try the dumbest thing you can think about. And then check where things can fail. Okay, so naively, quantum mechanics seems to be working. Is it? Then we have to want to check whether special relativity is actually working. Let's think about that. Okay, so then let's question, what about the special relativity? Right? And special relativity part consists of several things. First of all, we have to work to make sure Poincare invariance. Okay? And then we want to also make sure locality and causality. Not in a sharp, distinctive way, but in a rough sense. Okay? So we're gonna tackle these two questions one by one. Okay? At some point we will face a serious challenge. Okay? Now let's first talk about the Poincare invariance part. Is this working? At all? Oh, really? Okay. So let's check the Poincare invariance. So I suggested to take this as my Igor Hamiltonian, and then since naively on this, right? Oh, you can actually check more carefully by squaring this and then looking at that, and you can consider commute, right? So I suggest to take the same kind of momentum eigenstate as an energy eigenstate, right? And then proceed. Now, okay, so that will suggest that you can use the same orthogonality in completeness relations, right? And then expand any state in the Hilbert space in terms of this, taking this as your basis. Regarding the Poincare invariance, first thing you want to therefore check is that does this look like a Poincare invariant expression or covariant expression? Does that look like an expression which is good and consistent with the Poincare invariance? Does it? Well, even naively, this takes only 3 components, right? Yet, we talked about somewhat fancier object, so that is only 3 vector. But we talked about 4 vector, which had an energy component in it and the momentum. So certainly, this is treating only the 3 components separately without putting that in manifest. That one too. So maybe it is a Lorentz invariant and nice, okay, but that doesn't look at least like a Lorentz covariant or invariant. Okay? So let's make sure whether this is consistent with the Poincare invariance first. Okay? Then we may hope that looks, once we cure this problem, it may look like a Poincare invariant, probably unitary evolution, and then we might be able to ask the slightly more subtle question. Okay, so that's the plan. So let's check this. So in order to check the Poincare invariance, let's consider a particle. In this case, still relativistic particle on shell. Okay, so you may not heard of this word on shell unless you have studied quantum field theory before. So let me explain. So there's a notion, concept called particle being on shell or any particular physical state being on shell. So what does that mean? Okay, so suppose you actually have a relativistic particle, okay, with mass and then moving and momentum p as I described here. As we talked about, that particle has to fulfill this particular dispersion relation, okay? But we can rewrite that. So either on shell means that the particle actually satisfies that relation that I got there, or we can rewrite this in terms of the following expression. So p mu as a Lorentz invariant inner product modulo degeneracy satisfies this relation. So you can use this thing to check that. So they are not equivalent. They are not neither equivalent. But take this expression, and then if you impose the zeroth component of is positive, then these two are equivalent. Okay? Because neither if you solve this as quadratic equation, you get positive root and the negative root. And then obviously you force it to take positive root. Okay, then these two are equivalent. Okay? And whenever this 4 vector satisfies this constraint together with this, we say that that particle is on shell. Why shell? What kind of shell are we talking? Let me explain that. Let me keep this because I want to write a soon relativistic version here. So that's shell. What shell? Well, here is a diagram. So let me draw zeroth component here, and this is 3 vector. And then there is a like form. These are like form in a sense that p mu equal to 0. Okay. If you are confused by the 3-dimensional generalization, just take 1-dimensional version. Okay, that is literally then E0 squared minus E0 is equal to 0. So you have E0 to the plus minus p. Okay, so that's that. Then this on-shell condition give you a hyperbola. Actually, without that condition, that gives you 2 hyperbola. Okay. So here is the first hyperbola. And then this is the second hyperbola. So in a 3-dimensional picture, it's a shell. Okay, and that branch corresponds to the branch with this, that one with the minus root. So when I want to talk about on-shell relativistic particle, being on-shell, I'm talking about particles that can live on along this shell. Okay, so this is on-shell. Okay, so you have this hyperbola, not just hyperbola, a 3-dimensional hyperbola. Okay, so now I want to think about, what is the good integration measure consistent with the Lorentz invariance? What is notion of inner product and then a delta function consistent with the Lorentz invariance? That's what I'm going to think about. Well, in order to do that, let's just consider a f of p, where this is, I'm just taking a test function, which is a Lorentz scalar function. What it means is simply that if you take that function, transform under any kind of Poincare transformation, this basically doesn't change at all. That's what I mean. Okay? So then here I do. So let's first integrate over arbitrary, completely 4-dimensional momentum space. So here I'm treating entire 4 components, randomly, just integrate over entire thing. But I want to invent integration that is restricted along this on shell, which I can do it first by imposing p squared. So now, from now on, I'm just going to write p squared, and I actually mean carefully this, okay? Minus m squared. So I'm literally imposing that condition together with a positive root condition. So that together will give me physical on shell. Okay, I'm integral over on shell. And then f of k. So if I do that, you can see that I literally integrated over the on shell of any Lorentz scalar function, for instance. Okay, are you with me? So I'm just gonna now work out this thing a little bit. So I will have a integral over 3 vector, and the integral over energy component right here. And then delta function, this is 2 roots. And then together with this delta function constraint, you can convince yourself that P0 minus the vector square m square divided by 2 times. So this, I will explain, but probably some of you already see it. So where I got this, if you had a function, delta function with a function f of x, you have learned that you should expand over xi, where this is the zeroth of the function f of x, right? And then 1 over f prime evaluated xi, and then x minus xi. So you have seen this, right? I literally have done. So this has 2 zeros. One is positive shell, the other is negative shell. So I have to sum over those two, divided by the magnitude of the derivative of that function. So if you take a derivative, you will get that. Check it. But I'm imposing to get only positive shell. So I'm just taking a positive terms. Okay? I'm taking on its own. So now we can actually integrate over the zeroth component because now it's completely ready to integrate over the first delta function. So we can do that. Well, let me just continue the calculation here. So if I do that, I get the following, right? So 3 the vector, okay, and then the result of integration will give me. Let me just write this way. So now I will make sure what I mean by that, and then I have a Lorentz scalar, the scalar function of momentum for moment. And then by here, I have to be careful. EP is not a random function. It is a specifically on shell energy. Okay, so that's that expression. So what have I just learned? What have I just learned? I learned the following thing. Well, naively integrating over just the 3 momenta may appear to be not Lorentz invariant, right? Because I'm just treating only three directions separately. But by construction, I started my integration such that it manifestly Lorentz invariant. Meaning, under any Lorentz transformation, particle being on shell will never get out of this shell. Okay? So if you do any transformation, so suppose you started out with a particle satisfying this particular point, okay? With the momentum energy relation being that. And then if you perform any kind of a Poincare transformation, the particle only moves along this shell. Since you're summed over only that shell, by construction, this integral is Lorentz invariant. So that tells me that, well, this is the Lorentz invariant, and then the entire expression has been Lorentz invariant, which means that this measure is Lorentz invariant space-based integral. Okay, so this is Lorentz invariant, sometimes called space-based integral. Yeah. Yes.
This is really invariant under the non-order Lorentz group.
Non-orthochronous, you mean under the parity and so on?
Yeah.
Yeah, you have a reason to think that?
Because you mentioned that the first that if lambda 0 condition is not flipping the P0 function.
Yes. So here by which I mean okay, good. So he's asking. I told you that the Lorentz group has the 4 sectors. So Poincare group has the 4 sectors, right? There's a proper orthochronous, and they're flipped by parity and time reversal. And time reversal will flip the positive to the negative, for instance, right? So then I managed to, by injecting this, which is mostly for physicality condition, right? Because I want to look at the positive energy state. So that means that already I'm putting myself constrained into a proper orthogonal sector.
But you mentioned that if that factor is there on the Poincare group.
Yeah, Poincare, I still talk about taking a proper orthogonal sector supplemented with the translation. So that sector, okay, so good, thanks. So more precisely, together with the data function, I'm making sure that this integration is a Poincare there in a sense that it is a proper orthogonal Lorentz group together with the translation. Same with direct product with translation. Because the time t will flip here to there. So no proper orthogonal Lorentz transfer will take any state here, down state here. Okay? So therefore, we arrived at the fact that this, even though it's not clear, right, that this is Lorentz invariant measure, it is Lorentz invariant in a sense that I just explained. So we learned something. So instead of that, maybe it's a good idea to use that one. Okay, so that one is solved. So let's move on. I'm gonna solve the next one quickly, or you can just use this one because that's equivalent to that expression I just have written down. So let's now take care of delta function. Yeah, keeping this. So what about the delta function? That doesn't look like the Lorentz invariant in the product or sort of normalization. So to take care of that, let's consider the following. So this is just mathematically true statement, right? Before we worry about the Lorentz transformation, this is a true statement mathematically, right? And you see, again, I'm treating this is Lorentz invariant, if you like, or shell function, if you like. But now I know how to fix this problem after that exercise. I know how to make this measure Lorentz invariant. Done. And so this is Lorentz invariant. This is true statement. Okay, that must be Lorentz invariant combination. So here too, okay, instead of that, I wish to see 2e. Well, 2 is just just for the sake of it. Okay, number 2 is Lorentz scalar, if you care about that. So what really matters is that you need this factor, okay, to ensure that this is Lorentz invariant. In what sense? I mean the following. So if I have a p squared m squared, okay, factor if you want. I mean, you can put p prime if you want, and then k squared plus m squared is the same under, for instance, k mu is lambda mu p. That's what I mean. That doesn't change literally. Good. So we have figured out what are the good changes or improvement we want to make on top of this to make everything looks like Lorentz invariant expression. So let me just summarize therefore.
Can I have a question?
Yes, of course.
For now, we are constrained to the positive motion case, but
Yeah.
I did not find physical just reason because I also think that under the negative motion
Yeah.
would also have can also have physical meaning, but
Yeah.
for now we are constrained to the positive case.
Good. So there is a subtle discussion that we can make, and there is an obvious discussion we can make. What should we do? So if we start allowing negative energy, by negative energy we just mean more precisely energy being bounded from below. That's what basically I mean. Meaning I don't want to see my physics happening in a say energy structure. This is the energy structure. Suppose I want to do the physics here, but energy will never bounded from below. As you build up more and more physics intuition or actual like calculational experiences, physics is driven such that you want to sort of minimize energy of overall system. If you want, there's a more subtle version of that. Okay. Now, if your system, if you want to have a system, if you believe to be quantum system that doesn't have a energy which is bounded from below, then the system want to basically excite the mode with more and more negative energy, because that's more preferred. And so system goes through unstable evolution. Okay, you thought you prepared the vacuum state, but it will explode, producing negative energy state. That state will have a hard time having a genuine, proper quantum mechanical description. Okay, unless it is somewhat completely exactly solved, which I don't know example of. Okay, so there's this whole notion of instability of the description. So basically what I'm taking here, therefore, is that I imagine that my quantum mechanical system has energy bounded from below. For instance, for particle, single relativistic particle, I just mean that as you reduce extra three momenta, at some point it hit the lower bound of the energy, which is nothing but rest mass. And you cannot take the energy lower than that. And that's exactly described by this shell. Are you with me? This shell, right? And then energy is bounded from M and then upwards. This will take a nice quantum mechanical description. You want to say something?
I think that negative energy is in the full space diagram of negative time direction.
Yes.
But then the quantum mechanics and special relativity respect time reversal symmetry. So if you consider the symmetry, and I think that negative energy problem could be just a problem of convention.
I hear you. So what he was trying to say is that there's a negative energy, but also you might have or have a notion of, reversing the time flow. That will happen, okay? But not now. But when I draw that special relativity diagram, I meant there's a well-defined time arrow. That's why there was an arrow. There's a time in that world with the time defined to be flowing in the positive direction. I want to have energy bounded from below, and that will describe, if you like, particle. Later, we will introduce antiparticle. There, we will start seeing, okay, what if there's an antiparticle? Either you describe the negative energy flowing positive way or the other way. We will talk about that. Okay, but we are not ready to talk about it. Okay, so keep that in mind. Let's see how these notions are correctly assembled. For now, I'm just focusing on a single sector that has a well-defined time flow, only going towards the future. In that part, I want to only talk about the particle with the positive energy. Okay, particle. Good question. Any other question? Okay, so, right, let me finish my job. So then, we want to, now we understand how to make this looks like a relativistically invariant. So basically, I want to see that the orthogonality condition that it looks like. Let me just put SR just for now. That is relativistically nicely looking. I want to see this. V. No, not 2E. Not 2E. E minus Q. And that looks like relativistic expression. Then we have this. So these will be a relativistic analog. Okay? Now, I stick in 1 over 2 pi to the cube because I told you I want to dump every 2 pi's on the momentum side and not on the spatial position side. I told you that. Now, this can be achieved basically if you had a momentum state, which you use in law in a non-relativistic language, then you can just pass on to get relativistic version, if you just rescale the state, you see, you scale the state and then balance that by the rescaling factor here too. Basically, it just okay. So that's the cure we can do. Are you with me? So I just multiply by 2 pi to the 3 half plus so 2 pi cube. Then you might say, where's my 2 pi to the cube? Well, here you have. And then square root of the 2e both, so you get over 2e. Done. So here, you wanted to divide it by 2 pi to the cube, so you just distribute each of them, 2 pi to the 3 half, 2e, again, distribute equally. That's the scale you have to do to get relatively invariant expressions. Okay, so that's non-relativistic proof. Okay, good. So that's not a big problem. So where we started our story, so I wanted to have a quantum mechanical description of relativistic particle with Hamiltonian, which looked like in a three-dimensional sense. Okay, with some we have something that is okay looking quantum mechanically, but we had this relativity problem. The first part was Poincare invariance. I just cured it, right? Looks like it's okay. So what's wrong with that? So now let's ask the second aspect of special relativity, which was now causality. So is this quantum mechanical theory give us manifestly causal physics? Okay, let's ask that question. Now, in order to talk about causality, we have to talk about a position operator. Okay, so far we talked about momentum. We need to talk about the position operator. Why is that? Because. So now, here's my time, here's my space. Well, if you want, I mean free space. So now, suppose you are sitting here, or you're particle sitting here. And then, again, this is a light cone. These are light cone or x squared. Now, Lorentz sense is 0, or where here the stuff travels at the speed of light, right? Okay, now if you had a particle producing God, okay, you have a source. Boom, you produce the particle, whatever you think it is described by this physics. And then if that travels somewhere, and then you found a detector. So here's the source. Then you put a detector, and suppose you detected that particle. And then this is t comma x. The second time, you did the same experiment. Then you put the detector somewhere like here. Okay? Well, this is t prime and x prime. Right? We're questioning the following situation. So if this is what you get 100% of the time, then your physics is causal or consistent with the causality. Because they are connected by a propagation of information, propagation of the particle, for which the velocity, propagating velocity is less than c or maximally. Right? In order for this type of thing to happen, the propagation speed has to exceed the speed of light, and this is not causal. Okay? So to illustrate why this is really not causal, let's imagine the following thing. So I told you there's this shell, right? This is shell. This is only shell, right? And I told you that proper orthogonal transformation is supposed to only travel you from here to there, like that. And then there's this outside. Is this too busy? Or you can follow me if I draw something on top here. Can you? Okay. So if focused. So then there will be this part, which capturing things outside of shell, like this. And I think we will discuss in more detail explicitly, but it is possible to show that by Lorentz transformation, you can take event like here, and then reverse all the way to here, like for instance. So what appeared to be future by Lorentz transformation can turn into what appeared to be past, which is not causal. Okay? So that in a sense, if you see any event which is sitting in this what is known as the space-like separated region, because you can always bring what future-looking event into the what past-looking event by genuine proper Poincare transformation, it is not causal. Meaning it cannot be causally connected. That's what it means. And any such event can always be put also by, again, Lorentz transformation like that point, which is sharply just space-like separate. There's no causal and effect relationship. Okay? Something is so right now exactly the same point with me. There's no way I can affect that event or vice versa. Okay? So that's the sense this cannot be causal. Now we're asking, so any physics controlled by that gives me always zero probability density if I compute anything like this. That's what we're going to check. And I said that in order to add that kind of question, we need the position operator. Hopefully you see now what? In this description of quantum mechanics, I want to be able to say that, well, I prepared a particle here, and then I time evolve. And then I want to be able to measure something at particular position x, and then given time t. So I should be able to talk about the position, measurement of the position. So that's why we need a notion of the position operator. And for this discussion, I will just simply assume that such thing exists in a way that this is an old-fashioned quantum mechanical position operator. Xi, Vj, satisfying. Okay, I'm assuming that. And then we go. So to now tackle that question, let's suppose we prepare initial state, the initial state psi at t equal to 0, such that if I look at that, there will be completely localized at origin. Okay, so this completely makes sense. Okay. So then by position momentum relationship, you see that if this satisfies the normal looking. Okay, this is the normal looking thing. Okay. By the way, here I didn't specify if I'm talking about SR or NR. Okay. I'm talking about NR. So if you want to get SR, you just rescale. So this will be instead of that, there will be square root of T. Okay? So I'm gonna just use it, but final result will be the same, which I will stress again because that's important. Okay, let's move on. So then, just as a preparation, I can compute this, right? By inserting no, I don't want P. I mean X plus P here. So I know which state I prepared initially. I know this information, right? So you just plug it in. So that was X, and that was that. So if you compute this, what do you get? I think you get this. Yeah? Does that make sense? Does this, given this, does this make sense? Okay, why? Why physically that's something that you would expect. Modulo whatever the constant normalization. Why that makes sense? Because the calculation told you. But what is the physics inside behind this?
certain.
Yes, good. So I completely localize the particle in Poincare space. Then what should you expect in the momentum space, dual space? Completely spread, right? So absolute localization in the position give you complete non-localization in the momentum space, right? So that's why you should expect up to normalization. Okay, keep moving on. So next, we are gonna ask the real physics question. The real physics question is just for this. Okay, so can you see from the behind if I write down here? Okay, good. So then we're gonna ask the following question. So I start out with an initial state, right? And then I will time revolve with my lovely soon-to-be discarded Hamiltonian by time t, right? And then that was localized at x equal to 0. But then I'm gonna ask, okay, if I now ask, does that have a non-trivial overlap with x in such a way that the choice of x and t are such that this point is space-like separated from the region, right? That's the question I'm asking. Okay, let's do that. We need to compute this thing. Let's do it. So let's continue to compute this thing. So how would you do that? Well, I guess you can insert momentum completeness relation, right? That's what you do when you don't have a better idea. Quantum mechanics. You have experience enough. And so you know this, you know that because that's momentum against it, and then you know how to collapse that thing, right? So let me just write down the answer. It's obvious thing to write down. And you should get, because 1 over 2 pi this, and then another one from that, you get 2 pi to the cube. That's why I have a bar. Keep track of bars. So you should get this if you just plug in. Okay? Okay, some of you already see why this is rejected. Now, do you have a question? Are you happy so far? Yes.
타임 소스 마이너스 IH로 TL을 가요.
It could be. This is my convention, but I'm happy to switch. Yes, I have minus sign. Then that, right? Thank you. Thanks. Any other question? Good. Now, in principle or in practice, you should ask, well, you have not been using relativistically invariant expressions, right? Do I have to worry about that? Because whole point is make sure every single bit of spectral relativity is working, right? So do I have to worry about that? Just the fact that I'm not using that, relatively invariant expressions, could that give us wrong answer somehow? Right? That's a validated question. But you can check. So now you can just switch back everything special relativity, special relativity, special relativity, and you should get the same answer. So at least that cannot be the culprit behind whatever the result we're going to get after this. Okay, good. Now let's evaluate this. Now, I'm just going to set up the calculation to some degree, and then we will go live. Okay, so this square, good start. And then we're going to have V5, 0 to 5. P cosine theta. So let me take a set theta being the angle between this. So that would give me P r cosine theta minus I. Am I missing something? So far? Oh, and then this is minus 1. Okay. So we can first do this and then get rid of that. Square. And then, so I can do that. Then if I do it, I PR. Okay, so that's doable. And then this one, you can change P to minus P just to merge. Okay. So then I minus I squared, probably R. You can get it out if you want. Oh. Yeah. Okay. Yeah. Very good. And then IPR minus. Oh, probably not. Because I have done this. Now I have a 0 to minus infinity. Minus I can be flipped by changing the direction of the row. So I have now minus infinity. Okay? That's the integral we want to do. Okay? So far, just again, don't forget. I just want to compute this. Okay, so we just need to compute this. What's the big deal? Do it. Now, everything looks fine, but there's one thing that you want to worry about. So this is integral. And then the first thing you learn when you have to compute things like this is to check the analytic structure of the integral. Okay? Whether this is friendly object or nasty object, right? So let's check the analytic property of this integral. So nothing wrong here. So let's just check this. So if P is a P squared plus M squared. Now by P squared I mean 3 momentum, okay? Oh, that doesn't look good, right? That doesn't look good because this thing had a branch point at P. So you understand that by P I actually mean P dot P and then square. That's what I mean, okay? At the plus minus IN. So this has a branching point at the P is equal to plus minus IN. For those of you who haven't thought about this, actually, let me just remind you what do I mean by this. Okay? So what it means is that in the momentum space, in the complex plane of this three momenta, or if you just take a size of the momentum. So from now on, let me just consider the size of the momentum as a single variable. So this is a complex variable. And then you can rewrite EP as P plus IN, P minus IN, right? That works. If you just compute this, you literally get it. Okay? So it looks like this has zeros at either plus IN from here or minus IN from here. The problem, the culprit is that if you do the 2 pi rotation with respect to any of these 2 points, meaning either you take this and then go like IM, 2 pi up. So that's literally doing 2 pi I rotation. Are you coming back to yourself? You're checking single value of this one. Okay? The nature is that no, because of square root, exactly, you get I pi and then the same expression. So instead of when you go around the ones, this is the same point in the complex plane. So you expect that the quantity comes back to yourself, but instead you get minus E. So it doesn't go back to the value. So this is not single value, the function. But you see that if you instead have done it for pi I, now it goes back to itself. What it means is that this is a double valued function. So not just single round, you have to go around one more time. So technically, something has to be invented to avoid the problem. you have the same issue here. So this function is not single valued with respect to each of the point. This has a branching point. You say there's a branching point. Why? You have to branch it out. So as you turn around once, if you are not coming back yourself, you have to invent something called the branching curve to say that you're not going back to the same value. Instead, another sheet is attached like that. Okay? And then you go around the second sheet, and then you go back to yourself. So you have this branching point, so the branch curve, and then you have this another second branch curve, like that. So this is the analytic structure of this function, this integral. Okay? Good. Then what we have to do is that we want to compute, we have a third color. This is text. So we wanted to compute this integral, minus infinity to infinity, right? So with that singularity structure, this is integral we have. And in case you wonder, to be a good quantum field theorist, among many things, complex analysis is very, 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 very important. Okay? Because if you happen to read some good papers, deep papers, right? They were gonna write down some complex functions, and they would start talking about all physical minimum. Okay, oh, this is non-local, there's unitary isolation, blah, blah, blah. But oh, where did that all come from? Okay, so you want to sharpen out your complex analysis. Anyway, let's move on. So we understand what we have to compute. So in order to prove the causality, we need to compute that integral with this structure. Now, you want to see something happening to this contour, right? So either this will be closed up upward or downward. There's a binary choice. Why you want to close up? I'm like, oh, why this guy is trying to close up the loop? Let the contour leave alone. Why you want to close up? Well, because if you close up and there's nothing that's inside of the loop, the answer is 0. In complex integral, you have a loop, nothing bad inside, right? No simple pole, no double pole. Actually, double pole, fine. There's no simple pole, boom, 0, right? That's this Mr. Cauchy told us. So that's what we are doing. Let's figure out whether we have to close up upward or downward, that is. Well, we are doing integral in the momentum space, right? Sorry, yes, in momentum complex plane. And then, so that is this or that. Now, let's imagine it with m is 0. It's not, if it's totally fine, if it's not, I'm just simplifying the discussion. That looks like a P of R minus T, right? Roughly speaking. In the limit there, I'm just, you can forget about the mass. So then, which way you want to close, where if this P has imaginary part, because I'm going to explore entire complex plane, if this P has imaginary part, such that this thing has a convergence property, you want to pick up the imaginary part to be plus I something or minus I something? Plus I something, depends. That's true. That's true. Suppose I want to look at the space-like separation. The space is larger than time. And we can tell you this is positive. Now, the major part of the P should you want to be positive I something or negative I something? Positive I something. And then this is converted. All right? Good. That tells me that I want to close the contour like that, right? And branch cut just literally means that you're not supposed to pass. There's literally something else popping up like that. So you have to do this. This is not whatever you want to do. So suppose I call this path to be C1, C2, and C3, C4, C5. Okay? Good. So that's the stage we prepared. All three. Confirm me. Yes, very good. So then the contour integral from C1 to C6 of that thing is 0, right? By Cauchy theorem. No simple Poincare. And what we wanted to compute was the C1. Yes? And then the integral, which means that by this, I need to compute minus of C2, C6 of the same integral. Which means I just need to reverse the direction of a C2 to the 6. Basically, I need to compute that integral. Okay? And then you will check. You will check. Okay? Integral over C2 and C6, the large arc. And then integral over small arc, C4, all go to 0. So you will check, okay, in the whole problem, that is 0. This is because it's very large radius. This is because it's very small radius. So basically, we need to check, therefore compute this integral. So that is like what? Integral over that, and then that. But then I can reverse that. So integral of that minus integral of that, right? You mean? So integral of that minus that. That's like, oh, actually, I had to reverse the integral. Let me just. So therefore, the integral that we wanted to do, so let's now be therefore square, and then C1, which tells you what you're going to do, and then IPR minus I this. So that is equal to reverse, reverse. That means same contour and that and that. Okay? So that well, yes. Right? You with me? Okay, so this is equal to that. That. So I need to figure out a discontinuity across the cut. Right? So whether this theory, this physics, violates causality, if I take R minus T to be positive, so space-like separation, whether this thing describes a particle propagation that violates causality or not, all contained in this discontinuity across the cut. Okay? So let's compute that. Well, am I going to compute that? I can. Or are you going to compute that? I think you are not. Very good. There's an interesting thing to think about, but well, one more problem. So if you do the computation, so if you literally compute this minus that, then you should get the following answer. M infinite, because you're literally computing from this M to infinite. dy, like, so where did y come from? Well, that's why you're going to figure it out. Okay, so this, you will get this. Well, so as I go from here to there, basically I chose a path P. So how you're going to parameterize this contour? Well, now P is like I times Y, where Y goes to 0 to M to infinity, right? So I literally parameterize this, but then depending on which side of the curve, you will have either plus or minus epsilon, right? So that contour will be IY plus epsilon. This contour will be IY minus epsilon. Okay, it's a plug in and you have this answer. Now let's just stare at it. So y is virtually positive because I'm grabbing from the m to infinity. So these are positive. This is positive. And this switch function with a positive argument. I'm looking at the time positive. Okay? This is actually positive part that I'm looking at. So if you just integral, they will all add up, meaning zero chance for the cancellation. That means that this here will never give you zero probability. Even if you pick, oh, by the way, when I evaluate this, I already used the R minus C being positive. Okay? So that's what you get. So overall, the answer, we will look a little bit more. This will never be given. So this night trial of averting quantum mechanics to special relativity does not respect the causality, right? Relativistic causality. To illustrate the one conceptual point, let me actually compute. So I will do conservative estimation of this integral. Meaning the since part contains 1/2 e to the x minus e to the minus x, right? So I mean this is sine hyperbole. So I'm just gonna compute with only e to the x piece with the minus yr, okay? And then I'm gonna even drop the mass in the mass term because mass is not what's massing of the orbital quadratic. Even if it's a massless particle, we will have the same problem because square root of the p square still it has a branching point at the zero now origin. So still it has the same problem. So I'm just gonna take n go to 0, and then I'm just gonna take this part because this only reduces the overall value, right? So if I just now only integral over this part, I will get slightly overestimation. But let's just take a look at how bad the problem is, how bad a causality violation is. So if you just now do that computation, so again, with a simplification that first include only that, and then I'm just gonna take it equals to 0 limit. Then if you compute this, e to the minus I, because that's what we were doing with this localized at the origin, if you remember. If you do that, then this will be this 2 pi to r. Oh, you might say, well, the closure angle is 0 later. So this is a rough estimation of the calculation, okay? This is not strict calculation, but this is the exact so far, but I just quickly estimated. Now, why am I showing this calculation? So first of all, for space-like separation, right, or space-like separation. So starting from the origin, I'm looking at the point which is parameterized by r comma t or t comma r, which is space-like separated. For that, this is positive. You might say, causality violation, it happens, but it's not too bad. Should we really worry about it? But this is the explanation is suppressed, right? Especially if I start taking, this separation time n to be larger and larger, looks like it is very much suppressed. Isn't it? Not too serious problem. We really have to spend a lot of time curing this problem. And that's precisely why I even, spend time to write down this expression. What are we doing now? We are not doing some precision calculation of well-established theory. That's not what we're doing. What we are doing is what is the fundamentally correct way of describing the physics, right? We haven't completely invented it yet. But the course is about what is fundamentally correct way of synthesizing quantum mechanics with special relativity. We are asking that principal question, which means that you cannot take even exponential violation of any set of principles. Right? Is that clear what I'm trying to say? So I told you the following thing. It's not that you're given healthy theory and you want to compute some estimation of the quantity. That quantity may not be God-given exact value, right? You're going to get some estimation. You may compare to the data. They may not perfectly match. You may try to improve the calculation. You may try to improve the measurements. Okay, you may be happy with, okay, this is a, some percent precision. I'm pretty happy with that result. That's not what we are talking about. We are talking about even conceptually correct way of establishing and burning this big, field of physics, which means that construction does not allow single bit of mistake. It should be exactly zero. Okay, so that's why even if it is a small violation, that's absolutely not acceptable. Good. So last thing I want to say was, let's understand now in 5 minutes what went wrong, why we are getting this answer. Because now you have to go back and start asking yourself what went wrong in the construction. So let's summarize what we have done quickly, and then we will at least anticipate what should come next. So we said the following. Okay, what we have done as a trial of synthesizing our trial of putting this together, we say, okay, let me imagine I have a single particle of mass m. Then let's imagine that is described by this Hamiltonian. And then suppose there is a well-defined notion of a location or position of that thing in the form of a position operator. And then we ran the crank machinery to compute this causality, and then we found causality violation. Now, we can ask, what was bad in that trial? Which one has to be fixed? No single thing. So here is a Gedanken experiment. So let me just, I think invented by just for. So suppose you have a container. And then there's this piston. And suppose there's a one particle, for instance, bouncing around, whatever. Okay? And then suppose you hope that, first, can I measure the location precisely of this relativistic particle? You might say, oh, yeah, I know, at least I can say this particle must be somewhere by pushing it down, and suppose it can be also moved it like that, right? At that point, you can say, yeah, I know that particle should be inside. Sounds like I can do indefinitely precisely like that. It looks like there's nothing wrong. We're talking about single particle completely localized. Is this correct statement? Well, as we know, this. So if you try to push it down, delta x is smaller and smaller, you're getting this larger. And then this is roughly the same as delta E, as we talked about in relativistic regime. Which means you're given a more and more larger energy uncertainty, which means that out of the vacuum, you can start popping out particle productions. You're not talking about single particle location. So more precise single particle identification all of a sudden turn it into small zone, but unspecified number of particle compound. So you have to give up the notion of I want to describe a single particle if you want to go into this region. Okay? That's not possible. Okay? Once you start having relativistic energy, you have to give up on talking about specific single particle state. You should be ready to talk about many particles. Okay? That was the one inconsistency already built in. Second, as we talked about, this Hamiltonian has a manifest analyticity problem. And such a beautifully planned lecture. Entire causality violation in that particular calculation was captured by the discontinuity across the branch curve. That branch curve was already anticipated by this starting point. It looks like it's not good to use non-analytic Hamiltonian in general, non-analytic action as we will move into. It looks like we have to cure all those problems. So next time, therefore, we will take some time to fix this problem, okay? Well, let's first show this problem that how to deal with, how to describe physics of many particles. Okay, so that's inevitable derivative. Okay, so that's what we'll do next time, and I'll see you on Wednesday.